Hey folks, Mr. Bauer here. Today we're going to take a look at where did the formula for a derivative come from. So by now hopefully you know that magic formula that we have for finding the derivative. But yeah, where did it come from? Well, that's what we're going to find out today. So maybe first just a quick review, how to do it. So let's say we have this formula for x, for the position of an object, and we want to know its derivative, dx dt. Well, we've learned that the way to do it is real simple. Take the coefficient times the exponent. 40 times 2 is 80. And then reduce the power of the exponent by 1. From 2 we go to 1, we don't write the 1. So 80t. We take the next term then, same thing. 14 times that unwritten exponent of 1 is just 14. Exponent of 1 minus 1 is now an exponent of 0. Anything to the 0 power is 1, so we just have 14. And then the 50 would be multiplied by that invisible exponent of 0, t to the 0 power. And so the 50 times 0 is just 0. It drops out entirely. That's the derivative. It's easy to do, but where did that magic formula come from? Well, let's take a look. I think the easiest way to do this, here's our formula, is to see where that formula came from. It came from the actual motion of an object. I had a cart. I rolled it down a hill. I used a motion detector to plot its motion. Here's what the computer came up with. I had the computer plot a best fit line, and this is what the computer came up with. You might notice a little difference here. The computer's units are meters, so it's 0.40. I decided centimeters would be easier to use, so I have 40. Other than that, it's rounded off a little bit, but it's really the same equation. So let's approach this, first of all, by finding the average velocity between a certain time interval here for this graph. And ultimately we'll get to the formula for derivative. So let's say we take a look at 0.5 and we take a look at 0.1, and we want to know the average velocity between those 2 points in time. Well, the formula is delta x over delta t. But let's look at that another way. What we're really doing on this graph, delta x is the change in the vertical value. A more general way to write that is delta y. Delta t is the change in the horizontal value, and a more general way to write that is delta x. Well, you might recognize this as the formula for the slope of a graph, and that's really what we're doing here. We're finding the slope of this graph. Like, let me try to draw a straight line in here. I'll extend it a little bit. And so we are really finding the slope of that straight line right here. You can see really why it's an average velocity. Especially right in here, there's an area where the graph itself, the red line, is different from the slope line, the blue line. And so we are getting an average. We're not getting an instantaneous. We're not really getting the actual velocity here and here and among most of the curve. It's just an average. And so we've learned that with the derivative, what we can do is bring these 2 points a lot closer together. In fact, the idea is to really bring them on top of each other so that the delta t is equal to 0, which seems to be an impossible thing to do, but I'll show you how it actually works out in a moment. Before I get there, I want to do a numerical example. So let's find the average velocity between 0.5 and 0.6. So we've got a delta t here of just 0.1 seconds. It's pretty small, but it's not infinitely small. So I'm going to use our formula. And by the way, this is important. This is what we just found out also, that the derivative is the formula for the slope of a graph. That's always true. Whenever you find a derivative, you're actually finding the formula for a slope of a graph. Why do you need a formula for a slope? Because the slope isn't the same everywhere. The slope's low number here. The slope's a higher number here. So you need a formula. So let's find this average velocity now between 0.1 and 0.6. So here's our formula. Average velocity, delta x over delta t. In other words, that's your final x value minus your original x value divided by your final time value minus your original time value. And another way to write that is your x value at 0.6. That's our final x value, minus your x value at 0.5. That's our original x value, divided by our final time value, which is 0.6, minus our initial time value, which is 0.5. The bottom's easy to do. We get 0.1. The top, you got to work out a little bit. Let's do the top down here where I have a little more room. So delta x. So what's x at 0.6? Well, you just plug 0.6 into this equation. That's what I'm going to do right here. 40 times 0.6 squared plus 14 times 0.6 plus 50. That's x at 0.6 minus. Now I'm going to do x at 0.5. So x times 0.5 squared plus 14 times 0.5 plus 50. Now, I worked this out earlier on my calculator. You can check it if you want, but the answer there is 5.8. We then, if we want average velocity, divide by delta t, which we found up here is 0.1. And ultimately, that gives us 58. The units here would be centimeters per second, and that would be our average velocity. So that's how you do it with numbers. Let's take a look at how you would do the exact same thing with symbols. So there's our equation, there's our graph. But now I'm going to show you the power of symbols in algebra. I'm going to take the same 2 points, except now I'm just going to call this point t instead of calling it 0.5. And this point right here, it's a little different from this. It's delta t. So between 0.5 and 0.6 is 0.1. We can just call that delta t. That means that we could call 0.6 t plus delta t. That's what 0.6 is. It's t plus delta t. In our former example, it was 0.5 plus 0.1. Now, on the other axis, we need some x values. So over here, what's the x value? Well, it's just x at t. And what's this x value? Well, that's just x at t plus delta t. So those are our 2 x values. So now let's find the average velocity a little more symbolically. Delta x over delta t, or in other words, x at t plus delta t minus x at t divided by t plus delta t minus t. And again, we're getting all symbolic here, but if you look at the previous screen, it's really the same thing. T plus delta t was 0.6, t was 0.5, this was 0.6, this was 0.5. We're just doing it with symbols now. And again, the bottom is easy. T plus delta t minus t is just delta t. No surprise there. The top, it's a little trickier. Really, it's just a mess of algebra. So let me do that down here. Delta x. So now, instead of plugging 0.6 in for t, I have to plug in t plus delta t. I have to plug in some symbols. What's that going to look like? It's going to look like this. 40 t plus delta t squared plus 14 t plus delta t plus 50. All right, that's what plugging in t plus delta t to this function looks like. Now I have to subtract minus. Now I have to plug in t to this function, and well, that's really the way it is already. So I'll just rewrite the function, 40t squared plus 14t plus 50. Now, here comes the algebra. I'm going to do it slow. First thing I'm going to do is expand this binomial here. So this gives me a t squared plus 2t delta t plus delta t squared. Now take it easy. I'm not going to do anything else. I'm just going to rewrite what we already have up there. And then in the next step, I'll do some more simplification. You can see why we have a shortcut for this. You don't want to have to do this every time. All right, here we go. A little bit of simplification. I'm going to distribute that 40. So it's going to give me 40t squared plus 80t delta t plus 40 delta t squared. I'm going to distribute this 14. That gives me 14t plus 14 delta t Still have that 50 there. Now I have to distribute this negative sign. So minus 40t squared minus 14t minus 50. Whew, that's a lot, but we're almost there. And there's some cancellation we can do here. 40t squared cancels with minus 40t squared. 14t minus 14t. 50 minus 50. All right, where are we? Looks a little bit nicer now. 80t delta t plus 40 delta t squared plus 14 delta t. That's what that all reduces to. That's our delta x. Now let's go back and divide by, whoops, let's divide by our delta t. If I can get there, there we go. Delta t. I'm going to divide by delta t. That'll give us our average velocity. But maybe you notice every term on the top has a delta t. Let's factor that out. Just factoring out the delta t. So 80t plus 40 delta t plus 14 divided by delta t. And now that delta t cancels out. There's a delta t there. There's a delta t there. What's our final solution here? This is the formula for the average velocity. It's 80t plus 40 delta t plus 14. That's our formula for the average velocity. Let's take a look at that. All right, let me rewrite that. So our average velocity formula was 80t plus 40 delta t plus 14. And that really is a formula for average velocity. We could go back, and in our original example, we had 0.5, we had 0.6, we had a delta t of 0.1 between them. So we could stick in 0.5 for t. We could stick in 0.1 for delta t, and we should get an answer of 58 centimeters per second. So it's a formula for average velocity. But now, let's see if we can make it a formula for instantaneous velocity. How do we do that? Well, we want delta t to equal 0. If delta t equals 0, then we have a formula for instantaneous velocity. Remember, this is something we absolutely could not do on the previous screen. When delta t is equal to 0, you've got an undefined equation because you have to divide by 0. But what did we do over here? We canceled out the delta t that was on the bottom. And so now we're left with an equation that doesn't have a delta t on the bottom. I can make delta t equal 0. There. Doesn't affect these two. So what's our formula? This is our formula for instantaneous velocity. Because delta t equals 0, our formula is 80t plus 14. And that's exactly what we got when we used our magic formula. 2 times 40 is 80. Reduce the exponent by 1, you get t. And then you're left with a 14 for the next term. And so that's the reason why. It just turns out that every time you do this method with the delta t, it always ends up the same as if you just use that quick and easy shortcut.